We often picture the universe as cold and quiet, a black canvas scattered with distant stars. But when we look closer, we find something else entirely. From the shimmering rings of Saturn to the haunting glow of distant nebulae, the universe is a gallery of breathtaking wonders, each more surreal than the last. For millennia, we've mapped the stars and woven myths around the mysteries of the cosmos. The ancient Egyptians relied on the rising of Sirius to guide their calendar, while astrologers have sought meaning in celestial patterns since as far back as 3000 BC. Fast forward to today, and despite having access to everything, we still continue to be fascinated by space. And that's because the universe is absolutely packed full of really cool stuff. From awe-inspiring nebulae that wow us with their sheer beauty, to mysteries such as dark matter and dark energy that to this day have the planet's brightest minds completely stumped. In this documentary, we are going to see some of the most amazing and fascinating things that space has to offer. We will drift through the crimson clouds of the Orion Nebula, a nursery where stars are born in heat and shadow. We watch the pillars of creation, towering structures of gas and dust celebrated for their visual splendor. At last, we arrive at Hoag's object, a single, perfect ring floating in the dark, too symmetrical to be ignored, too strange to be explained. Each stop is different. Each one shows a new kind of wonder. These are the treasures of the universe, and we're just getting started. So let our journey begin. In the northern sky, tucked into the constellation of Pegasus, there's something the naked eye can't see. No brilliant color, no swirling arms or glowing gas. It looks at first like a mistake in a photograph. Just 5 tiny dots, 4 bright, 1 faint, arranged in a near-perfect cross. But if you know what you're looking at, those dots carry one of the most astonishing stories the universe has ever told. It starts not with the dots, but with the space between them. Roughly 400 million light-years from Earth, there's a galaxy. It's nothing unusual on its own, a hazy blur of stars and dust floating in the dark. But this galaxy sits directly in front of something much farther away, almost unimaginably far. Behind it, at a distance of about 8 billion light-years, is a quasar, one of the brightest, most violent objects in the cosmos. A quasar is what happens when a galaxy's central black hole starts devouring matter so fast it glows with the energy of 1 trillion suns. The light from that distant quasar has been racing across the universe for more than half the lifetime of everything, until it ran into something. It didn't stop, it bent. That foreground galaxy, by simply existing, by being massive, bent space-time itself. The gravity of its mass curved the fabric of space like a lens. The quasar's light, instead of moving in a straight line, followed those curves, around the edges, through the dips. And what reached Earth wasn't a single dot of light. It was 4. 4 distinct paths, all from the same source. 4 versions of the same thing, each arriving at slightly different times from slightly different angles, making a cross around the center galaxy. We call it the Einstein Cross. And it is not a trick. It is not a reflection. It is not some visual glitch of overlapping objects. It is light, ancient, furious, uninterrupted light, bent by gravity into a shape that looks almost too perfect to be real. Back in 1915, Albert Einstein laid out the idea. His theory of general relativity said that mass curves space, and light, which always follows the shortest path through space, would bend along with it. A few years later, this was tested during a solar eclipse when starlight was seen to bend slightly around the edge of the sun. But that was a tiny deflection. What Einstein didn't expect, what he once said would probably never be seen, was a full gravitational lens. Light so sharply warped by a massive object that it would split, multiply, and surround the lens like a halo. But then came 1979. Astronomers using the Kitt Peak National Observatory in Arizona found something odd. A quasar that seemed to be in 4 places at once. At first, no one could quite believe it. But by 1985, with better data and careful observation, the truth became clear. These weren't 4 different quasars. They were 4 views of the same one. The background quasar, the lensing galaxy in front of it, and the alignment of Earth, all lined up just right to paint a perfect cross in the sky. It became one of the most beautiful confirmations of Einstein's ideas. Not a number, not a formula, but a picture. A real image of gravity's subtle power. And here's where the wonder deepens. The Einstein Cross might look like 4 galaxies arranged in a perfect cross, but they're actually all the same galaxy, or more precisely, the same light from one quasar far behind it. The light has been bent by gravity as it passes around a galaxy in front, creating 4 separate images. But here's the strange part. Each of those 4 points isn't showing us the exact same moment, because the light took different paths to reach us, some longer, some shorter, some curving more. Each beam arrives at a slightly different time. Imagine shining a flashlight around a mountain, and the beams curve through different valleys. Some will reach you faster than others. Now swap the flashlight with a galaxy's light, and the mountain with gravity itself. That's gravitational lensing. So when we look at the Einstein Cross, we're not seeing one thing 4 times. We're seeing 4 versions of the same thing, separated by time. Like hearing the same voice shout across 4 different canyons, each echo arriving just a little later than the last. It's one of the few places in the universe where we can watch time itself, split and stacked in front of us. And there's even more happening under the surface. The lensing galaxy, the one doing all the bending, is not smooth. It's filled with stars, dust, gas, and dark matter. As those stars pass in front of the quasar's light paths, they create tiny, unpredictable flickers. This is called microlensing. To the naked eye, those flickers mean nothing. But to astronomers, they are pure gold. Each tiny change in brightness helps us map the internal structure of the lensing galaxy, how its mass is distributed, how dark matter flows through it. Even details about the quasar's own structure can be teased out from those changes. So in one image, a handful of faint dots, we get a cascade of discoveries. a quasar from the early universe, a foreground galaxy acting as a gravitational lens, 4 time-delayed views of the same object, and a chance to watch gravity in action, bending and shaping light itself. But the real beauty of the Einstein Cross doesn't come from the science alone. It comes from the shape. Because it's not just that the universe did this, it's that it did this with such precision. 4 perfect points, arranged in a pattern so clean and symmetrical, it looks like a symbol, a cosmic cross, a lens-shaped mirror holding 4 glowing shards of an object 8 billion years away. It's the kind of thing you might expect to see in a cathedral, carved into stone or painted on glass. Instead, it's drifting out there in open space. A geometric whisper from the laws of physics, hinting at symmetry behind the chaos. It reminds us that even in distortion, there can be harmony. The Einstein Cross is an accident in a way, a coincidence of alignment. The quasar, the galaxy, and us, all positioned just so. Move the galaxy a little to the left, and the illusion disappears. Tilt the quasar a little off-axis, and the cross becomes a blur. This perfect beauty exists because of timing, alignment, and gravity. And it won't last forever. Over millions of years, the alignment will drift, the image will warp, the cross will vanish. But for now, it's there for us to marvel. Now let's leave the illusion behind. We will be heading to a galaxy you can actually see, not with fancy telescopes or infrared filters, but with your backyard scope on a clear night. A galaxy so clean in shape, it looks drawn by hand. We're heading to the Sombrero Galaxy. They say the universe is messy. Explosions, collisions, chaotic swirls of gas and fire. But every so often, something appears in space that seems deliberate, composed, almost calm. If you ever point a telescope toward the southern edge of the Virgo constellation, you might find one of those rare sights. A small, faint glow at first, but once the image comes into focus, it's unmistakable. A bright white core with a dark, sharp-edged ring around it, like a coin dipped in shadow or a pearl wrapped in smoke. It's called the Sombrero Galaxy. And the name fits. It looks exactly like the wide-brimmed hat from which it gets its name. Not by imagination, but by structure. A thick, luminous bulge in the center, a perfectly defined band of dark dust circling the middle, and a wide, flat disk of starlight extending far beyond. In the emptiness of space, it floats there, perfectly posed. Officially, it's known as Messier 104. It was discovered in 1781 by French astronomer Pierre Méchain and soon added to Charles Messier's catalogue. But it wasn't until the Hubble Space Telescope photographed it in 2003 that the galaxy truly earned its iconic status. Hubble's high-resolution image revealed something far beyond what ground-based telescopes could see. Fine threads of dust, twisted like braided hair, silhouetted against the galaxy's burning center. The details were striking. The composition was unreal. And the internet took notice. The Sombrero became one of the most downloaded space images of the early 2000s. But what exactly are we looking at? The Sombrero Galaxy lies about 31 million light-years from Earth. That means the light reaching us now left the galaxy when saber-toothed cats still roamed North America. Astronomers classify it as an SA-type spiral galaxy. That means it has a large central bulge and tightly wound spiral arms, though from Earth's angle, we're seeing it almost edge-on, which hides the spirals and emphasizes the ring. That dark band isn't an outline. It's dust, cold, dense dust, stretching across the galaxy's disk like a ribbon. And even though it looks empty, that ring is full of motion. Radio telescopes have detected cold molecular gas hidden in the dust. This gas is the raw material for new stars. In fact, deep inside the dust lanes, star formation is quietly underway. Not in giant explosions, but in slow, steady pulses. Some regions flicker faintly in infrared, glowing with heat from baby stars still wrapped in gas clouds. These areas are invisible in normal light, but become clear when seen through telescopes like Spitzer or James Webb. So that shadowy ring isn't just decoration. It's a nursery, a cradle of light waiting to be born. At the heart of the Sombrero sits something enormous, a supermassive black hole. Based on the motion of stars near the center, astronomers estimate its mass at around 1 billion times that of our Sun. That makes it one of the most massive black holes known in any nearby galaxy. And yet, it's invisible. It doesn't shine. It doesn't roar. It simply pulls. It holds the center together with gravity so strong the surrounding stars circle it like moths around a dark flame. Beyond the bright disk, the galaxy stretches farther than it seems. Surrounding the visible part is a vast halo, a spherical cloud of ancient stars and globular clusters. More than 2,000 of these clusters have been found orbiting the Sombrero. That's nearly 10 times as many as the Milky Way has. These clusters are like fossils, dense, spherical collections of stars born billions of years ago. And their number hints at something unusual. The Sombrero might be more than just a spiral galaxy. It may also have traits of an elliptical one. That's led some astronomers to suggest it's a hybrid, a galaxy in transition. A possible bridge between two major galaxy types, neither one nor the other, just balanced. That's what makes the Sombrero so hypnotic. Balance. The symmetry is almost unreal. The galaxy looks as if it was sculpted, not formed. The bulge is centered. The disk is even. The light is smooth. It feels intentional, like a diagram. Like a model of how galaxies are supposed to look, clean, complete, and poised. Of course, the universe rarely cares about appearances. That precision is the result of billions of years of gravity. Nothing here is still, even if it looks that way. Every dot of light is a sun. Every lane of dust is moving. The calm we see is a kind of choreography, one held in balance by invisible forces. And that's what gives it beauty. Look at it long enough, and it starts to feel more like art than science. And yet, that beauty hides complexity. The dust ring isn't flat. It's warped slightly, twisted as if the disk was gently bent at the edges. That warp adds a touch of asymmetry, a reminder that no beauty is perfect. That even in the most symmetrical galaxy, there's a little bit of motion trying to push out of place, and the light from the center, that glow like a pearl, isn't pure. It's the combined shine of billions of stars. Some are young, some are ancient. Together, they form the nucleus. But what's most striking is how that core is framed, hugged on both sides by darkness. The ring isn't just dark because of dust. It's dark because the light behind it is being blocked. The dust acts like a silhouette, backlit by the starlight behind it. And the contrast between light and shadow is what makes the image pop. That's why it looks like a hat. That's why it looks like it's glowing. That's why it doesn't fade into the background like so many galaxies do. It's the contrast that gives it clarity. You can see the shape, you can guess the motion, but the details stay hidden. And that's part of what makes it beautiful. The mystery. Not everything is revealed. Not everything needs to be. Even now, with telescopes more powerful than ever, we haven't unlocked everything about the Sombrero. We don't fully understand how it formed, or why its halo is so populated, or what's really happening inside that massive black hole at its center. There's always more to learn, always more hiding behind the dust. But not all galaxies get to live that way. Some don't stand still. Some are pulled, stretched, broken, reformed, locked in constant motion. So we leave stillness behind now. We leave the clean lines and the quiet ring, and we dive headfirst into chaos, into a place where 5 galaxies are trapped together. Out in the quiet dark between galaxies, far from any sun or world, 5 galaxies hang in space like a frozen dance. From distant view, they appear peaceful, their glowing arms reaching toward one another, their halos overlapping and their starlight blending into soft trails. It feels like a cosmic gathering, but the silence is deceiving. Because not all 5 are truly part of the group. One is just passing by, much closer than it appears. And the others, they're locked in a slow, violent collision. Their gravity pulls them together, warping their shapes and stirring up vast clouds of gas that glow with the heat of impact. This is no gentle meeting. It's a beautiful disaster in motion. This is Stephan's Quintet, one of the most dramatic and beautiful gatherings in the known universe. The Quintet was discovered in 1877 by French astronomer Edouard Stephan, working from the Marseille Observatory. It was the first compact galaxy group ever recorded. At the time, telescopes couldn't show much detail. But even then, something seemed off. 5 galaxies, all clumped together, all faint. Decades passed before their true relationship came into focus. Turns out, only 4 of the 5 are physically close. The 5th, called NGC 7320, is much nearer to Earth, only about 40 million light-years away. It just happens to lie along the same line of sight. So while it looks like it's part of the group, it's not dancing with the others. It's a foreground actor, unrelated, but perfectly positioned to join the scene. The other 4 galaxies are the real performers, and what they're performing is a gravitational drama millions of years in the making. They are colliding, not quickly, not all at once, but over hundreds of millions of years. These galaxies have been pulling at each other. One brushes past, another dives through. Gas is stripped, stars are flung. Whole arms of starlight stretch like ribbons, trailing behind them like torn fabric in wind. These aren't gentle interactions. They're long, drawn-out battles, fought not with weapons, but with gravity, slow, relentless, impossible to stop. From Earth, the view is astonishing. Through a telescope, you can see them frozen mid-collision. Spirals smeared, tails of light unraveling into space. The colors are soft, washed by distance, but the forms are alive with motion. Some galaxies seem to fold inward, others stretch apart. The space between them glows faintly, not from stars, but from gas, heated to millions of degrees by violent impact. You're looking at shock waves mid-burst. One galaxy in particular, NGC 7318b, is slamming into the group at nearly 900 kilometers per second. That's fast enough to cross the United States in under 5 seconds. As it tears through the intergalactic gas between the other galaxies, it creates a shock front, a wall of compressed particles heated by collision. This isn't just light, it's fire on a cosmic scale. NASA's Chandra X-ray Observatory has mapped this region in glowing arcs of heat. The James Webb Space Telescope has revealed veins of star formation hidden inside the dust. Together, they tell a story. Galaxies crashing into one another, shaking loose clouds of gas that collapse under pressure and ignite new stars. Creation born from collision. It's not graceful in the traditional sense, but it is beautiful. This is not a picture of stillness, it's a painting of motion. Each galaxy plays a role. NGC 7319, for example, is home to an active supermassive black hole. A quasar, bright and loud, pulling in matter and flaring in X-rays. NGC 7317, the smallest, is rounder, more intact, a kind of anchor while the others spin. NGC 73, 18A, and B are the twin dancers, close in shape and locked in motion. Their collision is recent. Their trails are fresh. The scars of these interactions are called tidal tails, long strands of stars and dust that are pulled outward as galaxies tug on each other. Some of these tails stretch over 200,000 light-years. They curl and twist like brushstrokes flung across a canvas. In places, they double back on themselves, wrapping around voids of space. And embedded in these tails are pockets of starburst regions, small glowing clusters where new stars are forming in the wreckage. Webb's infrared instruments have seen through the smoke. They've captured these newborn stars shining through veils of gas. Because even as these galaxies tear each other apart, they're also making something new. This is also the future of our own galaxy. In about 4 to 5 billion years, the Milky Way will collide with Andromeda. Not with sound or sparks. Space is too empty for that. But with gravity. Our stars will pass through each other like ghosts. Tidal forces will stretch us. Some systems will be thrown into intergalactic space, Others will fall inward. Over time, the two galaxies will merge into one, a new, larger galaxy, shaped by chaos, balanced by mass. Stephan's Quintet shows us what that might look like. It's a preview, a mirror tilted forward in time. Eventually, the four true members of Stephan's Quintet will merge into a single, massive elliptical galaxy, larger than any of them are now. It will have a faint, ghostly shell around it, formed from the remains of stars flung outward in the dance. It will look nothing like the tangled cluster we see today, but its history will still be written in its shape. This transformation won't happen overnight. It's a slow, violent ballet playing out over hundreds of millions of years. Astronomers estimate that the final merger will take place over the next 1 to 2 billion years, depending on the orbital paths and velocities of each galaxy. The galaxies of Stephan's Quintet spin, crash, and reshape one another, but there's something underneath their chaos, something hidden in the rhythm of motion. So we leave the Stephan's Quintet and return to the visible. Our next destination is the place which is the most iconic image ever taken. We're heading to one of the most beautiful objects in the universe, the Pillars of Creation. Nearly 30 years ago, in 1995, NASA's Hubble Space Telescope captured an image that would become one of the most recognizable in astronomy. Towering columns of gas and dust in the Eagle Nebula, sculpted by intense stellar winds and radiation. Dubbed the Pillars of Creation, this image reshaped how we visualize star formation, appearing everywhere from textbooks to T-shirts. The Pillars of Creation was named one of the top 10 photographs from Hubble. These colossal structures reside in the Eagle Nebula, a stellar nursery about 7,000 light-years away in the constellation Serpens. A light-year is a unit of distance that represents the distance light travels in 1 year. Light travels at an astonishing speed of about 186,282 miles per second. In the context of the Pillars of Creation, which are located approximately 7,000 light-years away, this distance equates to nearly 41.6 trillion miles. This immense span underscores the incredible vastness of space and the time it takes for light to traverse even relatively nearby cosmic wonders. In 1995, the Hubble Space Telescope first revealed the pillars' beauty, making them famous worldwide. The enormous clusters of gas and dust have been compared to castles in the sky, cosmic stalagmites, or hints of a deep space coral reef. The tallest of these clusters is roughly 4 light-years from base to tip, or roughly the distance between Earth and Alpha Centauri, our nearest neighboring star system. Mostly made of gas and dust, these pillars are dense columns of interstellar material. Inside the pillars, gravity compresses pockets of gas and dust until nuclear fusion ignites, giving birth to new stars. Strong winds and radiation from these newborns shape the surrounding material, sometimes tearing it apart and other times triggering more star formation. This dynamic process makes the Pillars of Creation a stellar nursery, a place where the cycle of cosmic life unfolds in real time. These depict elephant trunks of interstellar gas and dust in the Eagle Nebula of the Serpens constellation. These elephant trunks had been discovered by John Charles Duncan in 1920 on a plate made with the Mount Wilson Observatory 60-inch telescope. They are so named because the gas and dust are in the process of creating new stars, while also being eroded by the light from nearby stars that have recently formed. The name, Pillars of Creation, is based on a phrase used by Charles Spurgeon in his 1857 sermon, The Condescension of Christ. The surrounding clouds of gas and dust are illuminated by the intense ultraviolet radiation emitted by huge newborn stars that ignite within the Eagle Nebula. The iconic appearance of the Pillars of Creation arises from this interaction, where the illuminated edges of the columns evoke images of ethereal fingers reaching towards the heavens. These pillars serve as a moving illustration of the cosmic symphony of creation, because they contrast light and dark, birth and destruction. However, the pillars' story did not end there. With Hubble and additional telescopes, scientists have revisited this area over the years, revealing fresh aspects of its history. Massive newborn stars, which are believed to be actively forming inside the pillars, were curiously absent from NASA's Chandra X-ray Observatory, which earlier in its mission searched for the high-energy signals of young stars inside the pillars themselves. This raised the question: are the pillars past their star-forming prime, since young stars are usually strong X-ray sources? Chandra can detect hundreds of very young stars in the area, as well as others that are still forming, called protostars, thanks to its keen X-ray vision. For those who don't know, what is a protostar? A protostar is a very young, still-forming star, the earliest stage of stellar evolution, that has not yet begun nuclear fusion in its core. It forms from a collapsing cloud of gas and dust and continues to gather mass from its surrounding molecular cloud, converting gravitational energy into heat. The protostar phase lasts until the core becomes dense and hot enough to ignite hydrogen fusion, at which point it becomes a main sequence star. Now back to the topic. More recently, NASA's James Webb Space Telescope in 2022 captured the pillars in infrared light, cutting through dense clouds of dust to expose intricate details of their inner workings. Webb's data showed vibrant new stars forming at the tips of the pillars, confirming that starbirth is indeed ongoing. The combined perspectives from Hubble, Chandra, Webb, and other observatories give us a more complete view of this stellar nursery than ever before. While the pillars of creation appear eternal in the image, the reality is that the scene is an illusion, a snapshot frozen in time. The actual region is dynamic and constantly changing due to the influence of the massive stars within it. The vast distance of the Eagle Nebula means that the light captured by Hubble took thousands of years to reach us. Thus, we see the pillars as they were thousands of years ago. There's also evidence that the pillars are slowly being eroded by nearby stars. Some astronomers speculate that a supernova shockwave may have already passed through the region, potentially destroying parts of the pillars, but because of the vast distance, we wouldn't see the effects for thousands of years. The pillars of creation are a breathtaking intersection of art and science. They show us that the universe is not just vast and mysterious, it's also profoundly beautiful. As our telescopes grow more powerful, we'll continue to peel back the layers of this celestial masterpiece, revealing secrets that have waited billions of years to be discovered. As we mark 3 decades since Hubble's first glimpse of the pillars of creation, we celebrate not just a single image, but an evolving scientific story, one that will continue to unfold with the next generation of space telescopes. What new secrets will they reveal? The universe holds countless masterpieces, each waiting for you to discover its story. A nebula is a cloud of gas and dust drifting through space, shaped by gravity, radiation, and sometimes the shock waves from dying stars. These clouds vary in type and origin. Some are planetary nebulae, formed from the outer layers of stars like our Sun as they reach the end of their lives. Others, like supernova remnants, are created in the violent explosions of massive stars. But some nebulae are just the beginning. Emission nebulae, like the Orion Nebula, are stellar nurseries, places where new stars are actively forming. Even though they can stretch across dozens or even hundreds of light years, nebulae are incredibly diffuse. They're not solid clouds like the ones in Earth's sky. In fact, even in the densest parts of a nebula, a single cubic centimeter might contain just 10 to 100 atoms, compared to 10 to the power of 25 molecules per cubic centimeter in the air we breathe. But when these clouds are bathed in the intense ultraviolet light from nearby young stars, something dramatic happens. The gas becomes ionized and it glows. The Orion Nebula doesn't quietly sit in the sky. It burns. It blazes like a living cloud, a luminous cavern of pink and violet gas set on fire by newborn stars. And yes, the Orion Nebula is hot, with parts of it reaching millions of degrees Fahrenheit and a general gas temperature of around 10,000 Kelvin, which is hotter than the Sun's surface. Through a telescope, it doesn't look like a star or a dot. It looks like a storm, frozen mid-motion. Ribbons of crimson and lavender stretch across a smoky backdrop, curling and folding in patterns too intricate for any artist to recreate. It's a painting that paints itself, changing with every passing moment of cosmic time. Located about 1,344 light-years away in the sword of the Orion constellation, the Orion Nebula, also known as Messier 42, spans roughly 24 light-years across and is one of the few nebulae visible to the naked eye. It's part of the larger Orion Molecular Cloud Complex, a sprawling region of gas and dust that's home to several active star-forming zones. The Orion Nebula is the closest giant H2 region to Earth, making it our clearest window into the process of star birth on a grand scale. At the heart of this swirling cloud lies something fierce and brilliant. The Trapezium Cluster, a tight group of young, massive stars that formed only a few million years ago. At its core are 4 primary O and B type stars, especially Theta 1 Orionis C, a star more than 30 times the mass of the Sun and tens of thousands of times more luminous. These stars flood the nebula with ultraviolet radiation, blasting nearby hydrogen atoms and stripping off their electrons. When the electrons recombine with protons, they release light, most strongly in the H-alpha part of the spectrum, around 656 nanometers, which gives the nebula its reddish-pink glow. This light doesn't spill evenly. The radiation carves out cavities and tunnels like wind through sandstone. Shadows of dark interstellar dust weave through the glowing gas, casting complex patterns and silhouettes. These aren't just empty spaces, they're cradles. Deep inside them, cold molecular clouds collapse under gravity, forming hundreds of young stars still wrapped in their natal shrouds. And within those dark lanes, something even more extraordinary spins into being. Protoplanetary disks, or propleids. First captured in detail by the Hubble Space Telescope in the 1990s, these small disks of dust and gas orbit young stars like halos. They're only about the size of our solar system, but they hold the raw materials for building planets. Some are already forming gaps, likely carved out by baby planets sweeping through their orbits. Each of these disks is a snapshot of a solar system under construction. A preview of what our own system must have looked like 4.6 billion years ago. In the Orion Nebula, we don't just see light, we see creation in progress, frozen in the middle of a cosmic sentence that has yet to finish. Some glow softly with scattered light, others cast long, tear-shaped shadows across the glowing gas. They're like tiny cradles, each one holding the early ingredients of planets, moons, and maybe millions of years from now, life. What's wild is how active this place is. This isn't a calm nursery, it's more like a battlefield of birth. The Orion Nebula is packed with Herbig-Haro objects, jets of matter that shoot out of forming stars. These jets scream through space at hundreds of kilometers per second. They smash into the surrounding gas and light up, glowing blue, green, or purple, depending on their composition. When you look at these glowing jets through the eye of a telescope, like Hubble or JWST, they look like beams of light pulled from a science fiction movie, thin, focused, and otherworldly. But they're real. They're the tantrums of stars still learning how to be stars. Everywhere you look, the Orion Nebula pulses with action. It's constantly being reshaped by the very stars it's helping to create. That's part of what makes it so paradoxical. The same radiation that makes the nebula glow so beautifully is also eroding it. The newborn stars, especially the ones in the trapezium cluster, send out such intense radiation and solar wind that they push away the gas that birthed them. In just a few million years, a blink in cosmic time, the glowing cloud will be gone. The stars will remain, but the veil that once cradled them will have vanished into the dark. And it's history that we've been watching for centuries. The Orion Nebula was first recorded in 1610 by the French astronomer Nicolas-Claude Fabry de Peiresc. Later, in 1659, Christian Huygens described it in detail, sketching what he saw and realizing it wasn't just a fuzzy star, but something much more complex. Back then, they didn't know they were looking at a stellar nursery. They just knew They were seeing something that didn't look like anything else. What makes the nebula even more striking is how it looks through different lenses. If you're an amateur astronomer looking through a backyard telescope, it appears ghostly greenish-white, like a smudge with structure. But with long exposure photography or space telescopes, its full spectrum bursts into view. Reds from ionized hydrogen, blues from oxygen, dark lanes of dust crisscrossing the canvas. It looks alive. You can even see echoes of larger cosmic processes within its folds. The way gas collapses and forms stars here is the same mechanism that formed our own sun about 4.6 billion years ago. The protoplanetary disks spinning quietly through the dust, those are echoes of what the solar system looked like before it had planets. And the radiation storms blasting away the gas, that's a glimpse into what might have shaped our own early planetary neighborhood. The Orion Nebula teaches us something rare in science, that creation is messy. It's not clean or peaceful. It doesn't happen in stillness. It happens through impact, friction, heat, and pressure. Beauty here comes from the struggle. Stars rip themselves into existence, and yet when they do, they shine. They shine so brightly that they burn shadows into the clouds around them, and they light up the sky for anyone on Earth with eyes and curiosity. That's what makes the Orion Nebula one of the most beautiful objects in the universe. It's not just color or complexity. It's the story, the motion, the raw, visible energy of creation. It's a place where light is born, shaped, and eventually freed. It's one of the only places where we can watch this happen in real time across the cold vastness of space. But this story of beauty isn't all about beginnings. Just as every star has a birth, it also has an ending. And that next part of our journey will take us from the fire of a stellar nursery to the quiet breath of a dying giant. In the cold silence of winter skies, one star pulses with a strange warmth. It doesn't sparkle like the others. It glows, deep and steady, like an ember at the edge of a fire. You'll find it at the shoulder of Orion, hanging low above the horizon on December evenings. That is Betelgeuse, a ruby-red flame, flickering faintly, never quite still. Sometimes it brightens, sometimes it fades, but it's always there, breathing. There's something haunting about its glow. Unlike the crisp, icy blue of Rigel, Betelgeuse has a softness to it, a red haze that hints at age. It's not a youthful star burning at full force. It's a coal in the cosmic hearth, glowing with memory. You can look up and almost feel it exhale, as if the sky itself is tired. Betelgeuse is a red supergiant, and that's not just poetic. It's a real stellar classification. It's nearing the end of its life, having already burned through the hydrogen in its core. Now, it fuses heavier elements, helium into carbon, and eventually iron, in a layered, onion-like structure deep inside. This internal pressure inflates the star to colossal size. If you placed Betelgeuse at the center of our solar system, Its outer atmosphere would reach somewhere between the orbits of Mars and Jupiter, about 1.2 billion kilometers wide at maximum estimates. That size makes it one of the largest visible stars in the night sky and one of the brightest red supergiants ever observed. It has a mass roughly 10 to 20 times that of the Sun, but its volume is hundreds of millions of times greater. Because it's so expanded, its surface gravity is weak. The outer layers are only loosely bound, making the star unstable and prone to shedding material into space. Its outer atmosphere is in constant turmoil. Massive convective cells, each the size of Earth's orbit, churn below the surface, lifting hot gas upward and allowing cooler gas to sink. These rising plumes create shock waves and launch stellar material into space in violent outbursts. These are not solar flares. They're more like massive surface eruptions, throwing billions of tons of gas out into the surrounding space at speeds of tens of kilometers per second. These events have been captured by space telescopes like Hubble, which in 1996 and again in later years recorded asymmetrical changes in Betelgeuse's outer atmosphere, blistered surfaces, and shifting brightness across its disk. The ALMA Observatory in Chile also imaged Betelgeuse in unprecedented detail, revealing cooler patches and arcs of gas expanding outward. These features are similar to sunspots, but on a much larger scale. Massive hotspots and cool regions that drift across the star's surface like slow-moving storms. All of this boiling and bubbling leads to something strange. Its light doesn't behave. Betelgeuse is a semi-regular variable star, meaning its brightness naturally changes over time. It cycles roughly every 400 days, with smaller fluctuations on shorter timescales. These are caused by both pulsations in the star's outer layers and changes in the distribution of hot and cool gas on its surface. Astronomers have known about its variability since at least the 1830s, and probably long before that. But in late 2019, something happened that caught the entire astronomical community by surprise. Betelgeuse's brightness didn't just dip. It plummeted, fading to about 35% of its normal brightness. For a while, it dropped from the 11th brightest star in the sky to the 21st. By early 2020, Betelgeuse had dimmed by more than 60%. It was shocking. Stargazers and professionals alike wondered if we were witnessing the beginning of a supernova. Headlines filled with the idea. Was this the moment? Was the great red star about to die? The event came to be called the Great Dimming. It drew attention from observatories around the world. The European Southern Observatory, NASA, and countless amateur astronomers pointed their tools toward Orion's shoulder. Would we see a star explode in real time? Later, analysis showed it wasn't death. Not yet. The dimming was caused by a massive surface ejection. A chunk of the star's outer atmosphere had burst off, cooled, and condensed into dust. That dust floated between us and the star, temporarily blocking the light, like a curtain drawn across a stage just before the finale. But even though it wasn't the end, the message stuck. Betelgeuse is fragile. It's old. And it's changing. The name Betelgeuse comes from Arabic, Yad al-Jawza, meaning hand of the central one. referring to its place in Orion. It's been known for millennia, catalogued by ancient Greek and Islamic astronomers, but it's only in recent decades that we've begun to understand what's actually happening inside. The star is in its final phase. It's burning through the last of its fuel, fusing heavier elements in its core: carbon, neon, and eventually iron. When the iron builds up, the fusion will stop, and the pressure from the core will no longer support the massive weight above. In that moment, the entire star will collapse inward in a fraction of a second. Then comes the rebound. A shock wave will race outward, tearing through the outer layers and ejecting them into space in a burst of light and energy. This is what we call a Type II supernova. And when Betelgeuse explodes, it won't be subtle. It will shine brighter than the full moon. It may even be visible in daylight for weeks. The familiar red dot in Orion's shoulder will become a new sun, briefly. That blast will not be destruction without meaning. The materials flung into space, iron, nickel, silicon, oxygen, will enrich the interstellar medium. They'll mix with nearby gas clouds, and in time, those clouds will collapse into new stars, new planets, maybe even new life. What begins in a dying star becomes the seed of something else. After the supernova, what remains depends on its mass. If it's not too heavy, Betelgeuse may leave behind a neutron star, a core of pure density, just a few kilometers wide, spinning rapidly and sending pulses of radiation into the cosmos. If it's more massive than we think, it could collapse into a black hole, a point from which no light escapes. Either way, what remains will be small and strange compared to the vast, bloated sphere we see today. But for now, it lives, and its beauty is in that living. Not the youthful, wild beauty of a star being born, like in the Orion Nebula. Betelgeuse is a different kind of beauty, the beauty of age, of fragility, of majesty with cracks in it. But sometimes, after the breath has faded, something unexpected remains. Not an explosion, not a giant, but an eye. A quiet, glowing ring expanding in space, watching. That's where we go next, to the Helix Nebula, to the Eye of God. It's hard to miss once you know where to look. Just below the constellation Aquarius, in the southern sky, lies a shape so haunting and serene that astronomers call it the Eye of God. Its official name is NGC 7293, the Helix Nebula. Located about 655 light-years from Earth, it's one of the closest planetary nebulae we've ever discovered, and through a telescope, it stares back. The Helix Nebula looks like an iris in the sky. At its center is a soft blue glow, almost icy, surrounded by rings of green, orange, and faint red. These colors aren't flat. They ripple outward in layers, like breath frozen in time. It's a spiral, but not like a galaxy's grand swirl. The Helix Nebula marks the death of a low to intermediate mass star, one that was once quite similar to our own G2 V-class sun. For about 10 billion years, it fused hydrogen into helium in its core, maintaining a balance between gravity pulling in and pressure pushing out. But once the hydrogen was depleted, the core contracted, and the outer layers swelled into a red giant, reaching hundreds of times the sun's radius. Eventually, the star became unstable and began shedding those outer layers, not in a sudden blast, but in repeated waves over tens of thousands of years. At the center of this cosmic unraveling lies the leftover core, a white dwarf, roughly the size of Earth, yet holding about 60% the mass of the Sun. It's incredibly dense. A teaspoon of its material would weigh tons. It no longer undergoes nuclear fusion, but it glows with residual heat, reaching surface temperatures of around 100,000 Kelvin. Over billions of years, it will slowly cool into a black dwarf, though the universe isn't old enough for any black dwarfs to exist yet. Surrounding this white dwarf is the nebula itself, a cloud of gas and plasma about 2.5 light-years across. What makes this gas glow is ultraviolet radiation from the white dwarf, which ionizes atoms in the surrounding cloud. When these atoms recombine with electrons, they emit light at specific wavelengths. Doubly ionized oxygen emits a blue-green glow. Hydrogen alpha emissions appear red, while ionized nitrogen adds subtle oranges and deeper reds to the mix. These glowing gases are what give the Helix Nebula its famous layered, eye-like structure, a spectrum of color wrapped in space. But the beauty isn't just in the color, it's in the structure. Look closely, and the rings ripple with complexity. That's because the dying star didn't expel its gas evenly. First came slow winds, measured at speeds of about 10 kilometers per second, which flowed outward steadily during the red giant phase. Later, as the core heated and collapsed into a white dwarf, it released faster winds, blowing out at over 100 kilometers per second. These fast winds overtook the slower ones and slammed into them, creating shock fronts. The result? Concentric shells and arcs, each recording a chapter of the star's slow death. But the real wonder lies inside those rings. Scattered throughout the nebula are cometary knots, dense, dusty clumps of gas, each about 100 billion kilometers wide, roughly the size of our solar system. They have bright heads and faint tails that always point away from the white dwarf at the center, shaped by the radiation pressure and stellar winds. They're not racing through space. They're mostly still, slowly dispersing. But the way light hits them makes them look like frozen comets mid-flight. The Hubble Space Telescope captured these knots in detail in 1996, revealing thousands of them, each with its own delicate shape. Some are tightly packed, shielding their interiors from harsh UV radiation. Others are more diffuse, already starting to dissolve. These knots may be responsible for some of the clumpiness seen in other planetary nebulae and could even influence how material is recycled into future stars. In total, the Helix Nebula is thought to be only about 10,000 years old, a newborn ghost in galactic time. Eventually, the gas will drift away and the glow will fade, leaving only the white dwarf to cool in silence. But for now, we catch it mid-breath. The last glowing sigh of a star that once burned like ours. The helix was first recorded in the 1820s by German astronomer Carl Ludwig Harding. It was later studied in greater detail throughout the 19th century as telescopes improved. Astronomers quickly realized it was something special. Its proximity, just about 655 light-years away, makes it the closest bright planetary nebula to Earth. That makes it incredibly important for science because it gives us a detailed view of what happens when stars like the Sun die. The name planetary nebula is misleading. It has nothing to do with planets. Early astronomers like William Herschel used the term because, through small telescopes, these glowing disks looked like planets. Round, smooth, and colorful. But what they really are is death caught in slow motion. And the Helix Nebula is perhaps the clearest window into that process. That's what makes it one of the most beautiful objects in the universe. Not the brightness, not the scale, but the emotion it stirs, the calm it gives. One day, billions of years from now, our sun will follow the same path. It will expand, then let go. And what remains will look much like this: a white dwarf, a halo of gas, a painting made of atoms. This is the fate of solar systems. This is the final story most stars tell. And now, we leave this gentle glow behind. We've seen the birth of stars, and we've seen them fade, but what happens when there's no star at all? No creation, just emptiness. Beyond the light of nebulae, beyond the whispers of white dwarfs, lies something deeper. A place not made of things, but of absence. A hole in the structure of the cosmos. There is a kind of beauty that doesn't shine. It doesn't sparkle, or flare, or color the sky. It doesn't swirl like a galaxy, or burn like a star. It simply waits, quiet, vast, and still. That is the beauty of the Boötes Void. A silence so complete, it feels sculpted. A structure not made of stars or gas, but of absence. Discovered in 1981 by a team led by Robert Kirshner as part of the Harvard-Smithsonian Center for Astrophysics Redshift Survey, the Boötes Void wasn't first seen through a telescope, but revealed through redshift data, measurements of how galaxies move due to the expansion of the universe. Astronomers were building three-dimensional maps of galaxy distributions to trace the large-scale structure of the cosmos. One part of the map stood out, a region more than 300 million light-years across, where virtually no galaxies appeared. To put that in perspective, if you placed the Milky Way at its center, you'd need to travel about 150 million light-years in any direction before reaching a rich cluster of galaxies. The Milky Way itself is roughly 100,000 light-years across, so the Boötes Void is thousands of times larger than our galaxy, and yet it contains almost nothing. In a universe where a typical volume of this size would contain thousands, even tens of thousands of galaxies, the Boötes Void holds fewer than 60 known galaxies. That number isn't zero, but it's astonishingly low. The void isn't a perfect sphere either. It's irregular, asymmetrical, shaped more like an ancient crater than a clean bubble. When plotted in 3 dimensions, it opens like a cavern inside the cosmic web, the vast filamentary structure made of dark matter, gas, and galaxies that forms the skeleton of the universe. For cosmologists in the early 1980s, the Boötes Void was deeply puzzling. At the time, models of structure formation were based on cold, dark matter, a theoretical form of matter that doesn't emit light, but helps explain how galaxies clump under gravity. In these simulations, voids existed, but nothing as large or empty as Boötes. It was too big. It was like mapping a forest and suddenly finding a missing continent. To explain it, some scientists proposed the void merger hypothesis, the idea that the Boötes Void formed from the gradual merging of multiple smaller voids over cosmic time. Like bubbles in rising dough, these smaller regions of emptiness could have expanded and blended together as the universe stretched, with dark energy accelerating that expansion over the past 5 billion years. The result would be a compound void, a patchwork of emptiness, joined and amplified. But other researchers suggested something deeper, that the Boötes Void might trace its roots to the very birth of the universe. According to this idea, the Boötes Void might not have formed later from galaxies moving apart. Instead, it could be a leftover mark from the very beginning of the universe, shaped by tiny, random bumps in energy that appeared just after the Big Bang. These bumps, called quantum fluctuations, were incredibly small at first, but they got stretched and blown up during a moment of rapid growth called inflation, which happened just a tiny fraction of a second, about 10 to the minus 36 seconds after the universe began. So the void might be a frozen trace of something that happened before stars or galaxies even existed. These ripples are now visible in the cosmic microwave background, the afterglow of the Big Bang. If this theory is right, the Boötes Void might not be a late-arriving accident of galaxy evolution, but a fossil of the universe's earliest structure. There's a strange kind of poetry in that. Most people picture space as empty, but in truth, the universe is incredibly structured. Galaxies don't float randomly. They align along filaments, connect at nodes, and surround voids like the bubbles in a cosmic foam. Even most empty regions of space contain sparse matter, isolated dwarf galaxies, diffuse gas, and dark matter halos. But the Boötes Void is different. It's empty in a way the rest of the universe isn't. The Boötes Void still has gravitational influence precisely because of what it lacks. Dense regions of the universe pull harder, so the void's relative lack of matter causes galaxies on its edge to be pulled away from it, a phenomenon known as peculiar velocity. This motion isn't caused by expansion alone, but by local gravitational imbalances. Like water sliding away from a drained well, galaxies migrate toward higher density regions, leaving the void emptier over time. This behavior helps scientists study cosmic flows, the migration patterns of galaxies across billions of years. By measuring the motion of galaxies near and around the Boötes Void, astronomers can refine models of dark matter distribution, void evolution, and the behavior of dark energy. These vast emptinesses aren't just holes, they're part of how the universe organizes itself. The Boötes Void reminds us that absence can be as meaningful as presence. That silence can speak. And that even in a universe defined by light and matter, it's the darkness in between that holds the shape of everything. The name Boötes refers to the constellation where it was discovered, near the herdsman's star Arcturus. But the word itself echoes boot, as in a kick. It feels like the universe stepped on the floor of space and left a dent, a footprint that never filled back in. From this vast absence, our next step feels sharper, more focused, because after looking into the void, even the smallest symmetry catches our eye. Now we turn towards something completely different, not enormous, not empty, but precise. A circle of stars so perfect, so uncanny, it almost looks artificial. In a universe full of spirals, clouds, and chaos, Hoag's object is a perfect circle. It doesn't twist or arc or sprawl like most galaxies. It sits alone in the black, quiet and precise. Imagine a glowing golden sphere, old and steady, surrounded by a flawless blue ring of new stars, wrapped around it like a halo. There's nothing messy about it. No tails, no warps, no companions tugging at its edges. Just a ring so round, it looks drawn by hand. It's as if the universe paused, took a breath, and traced a single shape with absolute calm. That's Hoag's object, also catalogued as PGC 54559, a galaxy so symmetrical, so still, it feels like a secret. Arthur Hoag first spotted it in 1950, while examining photographic plates at the US Naval Observatory. At first glance, he thought it might be a planetary nebula, possibly the glowing shell of gas surrounding a dying star. But further observations quickly revealed the scale. This wasn't a nebula, it was a galaxy, and a bizarre one at that. Most galaxies fall neatly into the Hubble classification scheme. Spiral like the Milky Way, elliptical, which are more rounded and filled with older stars, or irregular, often shaped by collisions and gravitational interactions. But Hoag's object didn't fit. It had a nearly spherical core resembling an elliptical galaxy, but surrounding that was a striking, detached ring of bright blue stars, a nearly perfect circle. That outer ring spans about 120,000 light-years in diameter, slightly larger than the Milky Way. The inner core measures around 17,000 light-years across. Between them lies a vast, dark gap, a near-empty region tens of thousands of light-years wide. That's not typical. In ring galaxies formed by collisions, you often see wisps or streams of stars, what astronomers call tidal tails. But Hoag's object shows none. The ring is clean. There's no visible bar structure in the center, no distorted spiral arms, and no nearby galaxies that might have caused the formation. It floats in relative isolation, about 600 million light-years away in the constellation Serpens. The ring itself is packed with young, massive stars, bright blue O and B-type stars that burn hot and live fast. Ultraviolet imaging from the Galax Space Telescope confirms that star formation is actively taking place in the ring. By contrast, the central core contains older, redder stars, typical of an evolved elliptical system. Spectroscopic data shows little gas in the core, indicating star formation there ceased long ago. The contrast, old golden core, young blue ring, makes Hoag's object one of the most colorfully structured galaxies ever observed. It's not just the symmetry, it's the timing and balance. That cool gold at the center, steady and aged, surrounded by the icy blue light of youth. It's like time itself has been painted across the sky. Hoag's object isn't beautiful because it's dramatic. It's beautiful because it's calm. It doesn't scream for attention. It hums. The mystery of its formation still isn't fully solved. One theory suggests a long-ago head-on collision with another galaxy, where the intruding object plunged through the center and triggered density waves that pushed gas outward in a ring. This process can create what's known as a collisional ring galaxy, but most galaxies that form this way show structural distortion or remnants of the intruder, and Hoag's object shows neither. It's too pristine. Another idea points to secular evolution, slow internal changes that cause bar instability, where material moves outward and collects in a ring. But again, Hoag's object has no bar. So some astronomers suggest it could have formed through a multi-stage process, with the ring forming later by accretion of cold gas from the surrounding intergalactic medium. Over time, that gas cooled and collapsed into stars. Yet even this doesn't fully explain the perfect symmetry and gap between the ring and the core, which remains unnaturally clean. That gap, tens of thousands of light years wide, is one of the most striking features. The ring is rotating, held in orbit by the mass of the core and dark matter halo surrounding the entire system. Spectral data shows the ring's rotation speed is consistent with stable, long-lived motion, meaning it has likely existed for hundreds of millions of years, if not longer. And behind Hoag's object, if you look closely through the open space of the ring, you'll see a smaller ring galaxy, faint and distant, a perfect echo. First noted in Hubble Space Telescope images from the 2000s, this background galaxy adds another layer of wonder. It's not connected to Hoag's object, just perfectly aligned, like the universe made this one perfect shape, and then let its reflection travel even further into space. Some have compared it to a mandala, the sacred geometry found in human meditation. Others see it as a cosmic eye. Some see a symbol, or a loop, or a doorway. It invites interpretation. It doesn't tell us what it is. It just shows us and waits. We don't know how long Hoag's object will stay this way. The stars in the ring will burn out over time. Gravity could slowly erode the shape, but for now, in this moment of cosmic time, it holds. And so, we end where chaos becomes symmetry, where galaxies drift into silence and light folds into meaning. We've wandered through stellar nurseries, where light is born in violence, through the red pulse of dying giants, through clouds shaped like eyes, and into the deepest quiet the universe offers. Each stop gave us something different, but together they told one story. That beauty in the cosmos isn't rare. It's everywhere, written into gas and gravity, into decay and creation. What we've seen isn't decoration. It's the result of physics unfolding over billions of years. Rings form because stars obey momentum. Nebulae glow because light escapes dying cores. Even the great voids exist because matter gathers elsewhere. These shapes, colors, and silences aren't accidents. They are the echoes of motion, written in light. The universe doesn't need to repeat itself to be consistent. It doesn't create copies, it creates patterns. And in those patterns, beauty emerges. Not because the universe tries to be beautiful, but because it can't help it. From the smallest dust knot to the largest galactic arc, there's meaning in the way things are shaped. You just have to look long enough to see it.